Hello, everyone. Thank you for joining us for another live webinar session hosted by Tech and All About Circuits. My name is Dale Wilson. I'm the Director of Engineering and Content for Tech and All About Circuits, and I'll be your moderator today. Today's session is brought to you by Vishay and is titled Explore eFuse Reference Designs for Load Monitoring and Protection in eMobility Applications. Let me tell you about our presenter. Vince Avalar is a Field Applications Engineer for Vishay Intertechnology. He oversees application engineering and business development for the western coast of the Americas and Mexico for all of Vishay's automotive products. Vince received his bachelor's degree in electrical engineering from California Polytechnic State University in San Luis Obispo. He initially worked as a service engineer in the power conversion industry and then became an applications engineer for a power supply company. Following the presentation, we'll have a live Q&A session with Vince. You can submit your questions at any time during the webinar using the Q&A section on the right-hand side of your screen. Near the end of today's presentation, you will be able to find the presentation slides under the Handouts tab near the end for download. Thank you so much for joining us, and with that, I'll hand it off to Vince for today's presentation.
Hello, everyone. Welcome. Thank you for joining this webinar. As mentioned before, we're going to talk about our eFuse reference designs. So let's get started. So here you can kind of see the 48 volt bus as illustrated. Tesla Cybertruck is an example of an electric vehicle that adopted this new architecture that used to be only 12 volts to power various loads from the low voltage power battery. The 12 volt bus is not going away. It's still used to take care of the low power loads such as lighting and infotainment. The 48 comes into play for the power hungry loads like power steering or air conditioning. With higher power, we get lower current, resulting in thinner wires. Our eFuse was designed to safely switch these loads. More on this later. Stepping up the voltage, here we see the same idea of power distribution to loads. Here we see the high voltage battery that could be 400 volts or 800 volts feeding a power distribution unit before getting to the high current loads. This power distribution unit used to be only made of high power contactors and old school fuses. The downside to these components is that they're not resettable and they have a very slow response. Vishay's eFuse design takes care of these issues. Here's an illustration of the mechanical relays that we're discussing. In the following slides, we're going to look at another reason for the growing need to replace these conventional relays with new methods for the purposes of life expectancy and safety. Here you can see a mechanical relay, and here's the big deal. An electric arc is created between the two contacts when the relay starts to open, when the voltage and load current are present. This arc quickly disappears as the relay completely opens. So this is a major deal here. In summary, what I'm trying to say is mechanical relays can become more expensive with the additional design considerations to mitigate the arcing mentioned. Even with arcing protection, the life expectancy is still reduced for these contacts. So, to maintain the life expectancy and safety requirements of a vehicle, Vishay developed eFuses with our unique electronic switches that are resettable, used for various voltages and currents. So many flavors. This is the 48 volt version. How high of loads? It's been designed to switch loads up to 200 amps, and it works with a standard double-sided FR4 printed circuit board with passive cooling, so no need for an external heatsink. The design also features a pre-charge function and continuous current monitoring for control and protection. Like I mentioned, we have different flavors of the eFuse, not only for a 48 volt bus, but here we can see the 400 volt version for loads up to 100 amps. We also have an 800 volts, 50 amp version of our eFuse. In this presentation, I will highlight some of the key differences, such as having optoelectronics for isolation and safety. Here we can see both sides of the printed circuit board. On the top, you see that most of the high voltage circuitry is located with connectors, control buttons, status LEDs. And on the low voltage control circuitry is located on the bottom side. If the current exceeds a predetermined limit, the load is quickly disconnected from the high voltage source to protect both battery pack and the user. The eFuse can also detect excessive low capacitance or a short circuit during a power up and intermediate shutdown. As you can see, many features are available compared to the traditional old school mechanical relays. This is a very high level schematic of the power stage of our 400 volt eFuse. The high voltage battery input is on the left side and the output voltage to the load is on the right. In later slides, we'll explore the components in more detail, which highlight Vishay's rich portfolio, which can populate most of a PCB. As previously seen, the main high voltage power stage components are located on the left-hand side of the top of the board. The low voltage control circuitry is located on the right-hand side of the bottom of the board. What's highlighted here is the isolation barrier, which separates the high voltage from the low voltage for safety purposes. More on this later. A similar schematic can be seen for the power stage for the 48 volt eFuse. The 48 volt battery input is on the left, and on the right you have the output. So here you can take a look at the layouts. The main power stage components are located on the left of the board, on both the top and the bottom, and most of the control circuitry is located on the right-hand side. This is just to get a feel for where everything is located in the eFuse's reference designs. Okay, so getting into the components. So who's handling all the switching of the high currents up to 200 amps that we have discussing? Well, the answer is MOSFETs, which I highlighted here in the schematic. Please note that this is a bidirectional connection to handle the high load current. And since this is very high current, you can see here that we're using 10 of our Vishay power MOSFETs in parallel. The part number for our MOSFET is the SQJQ160E for each direction. This is where you can find it in the layout. On top, you can see the 10 parallel connected MOSFETs for one switch. And then on the bottom, you can see the other 10 parallel MOSFETs as well on the bottom side. More details on the Vishay MOSFETs used for this design. This is our trench technology in our power pack 8x8 millimeter package that features bond wireless clip construction instead of wires. What's the key benefit? This improves the thermal performance and also has like a higher efficiency with less losses. As you can see here, the gold wing provides a stress relief for applications that heat cycles to prevent solder joint degradation, to improve board level reliability, very important under harsh under the hood conditions. It is also worth mentioning that Vishay has a top-sided or reverse cooling package available. Instead of dissipating the heat down into the board, you dissipate it upwards to a heatsink. Vishay started as a resistor company through acquisitions. The portfolio was built, but so there are several resistor technologies that we're using this eFuse reference designs. For instance, here you see the gate resistor. It's a thick film. A thick film is typically considered. However, the pulse capability was a key consideration for this application. So we need a technology that could handle the large pulses better than your standard thick film. So in this design, the thin film melt technology was selected, the MMU series from Vishay, available in 3 different packages. The 0102 package was selected for this particular design. Due to the amount of the extra surface area, as you can see here in the diagram, compared to the standard flat SMD, the pulse capability is highly improved. Also very stable technology, which means that the resistance value does not drift very much with time or temperature. There is a wide range of resistance values that you can find here. To protect the battery, the vehicle wiring, and any damage to the load in case of a short circuit, the load current is continuously monitored using a shunt resistor labeled R5 in this schematic, which is located between the two sets of the MOSFETs. This is where you can find the shunt resistor in the layout. As you can see here, is between the two sets of power MOSFETs. In this design, a Vishay power metal strip resistor, the WSLP 3921, was selected with a 100 micro ohm value to minimize power dissipation. All right, taking a closer look at current sense. Current sense is needed to monitor for control purposes or overload protection. There are two methods for accomplishing this: the resistive current shunt, like the one we use, and a Hall effect. There are pros and cons between these technologies, but there are several disadvantages with Hall effect, which are listed here. The key ones are with respect of accuracy, delay, and higher cost. Several packages are offered for current sense resistors, which includes large battery shunts for a different application. As mentioned before, the WSLP 3921 was selected in this design. The Vishay power metal strip design features an all-metal welded construction, so no substrate. WSLP also features a high power density compared to our standard WSL. For the 100 micro ohm selected, it offers a higher power rating, up to 9 watts for this package size. If a higher power is needed, the WSLP 5931 could be used. Also, we have a different variation for the shunts. The WSLT 3921 provides an extended temperature range up to 275 Celsius. Still in current sensing, here's a view of the current sense amplifier that was used for this very small voltage in millivolts to amplify the voltage level and use for control and protection. In this case, the amplified voltage is fed into both the microprocessor for current monitoring and also the competitor circuits for overcurrent detection and short circuit shutdown. As you can see, many features compared to the mechanical relays that we talked earlier in the presentation. So one of the key differences with the higher voltage is that the voltage must pass from the high side to the low side through the isolation barrier. To do so, an optocoupler was used, which we will discuss in later slides. In the 400 volt eFuse, an isolation barrier is required for safety purposes in terms of protecting the user from potentially getting in contact with high voltage as a result of failure of the hardware. Galvanic isolation is required in this type of applications. The low voltage circuitry must be completely separate from the high voltage. In this design, Vishay is using a high-speed linear optocoupler. This is used in the bottom part of the schematic for one of the voltage measurements. Here you can have the visual of the component. This is the Vishay VOA300 linear optocoupler. You can see the specs here. It offers 0.01% linearly and high gain stability over temperature to maintain a very precise voltage measurement as it passes across the isolation barrier. The 1.4 mega hertz bandwidth is less than 2 microseconds response time for a high-speed response. This optocoupler is rated at 5300 volts RMS for isolation voltage with either a DIP8 or SMD package. All right, to finish current sensing, a matched pair of resistors shown in the red boxes were used on the op-amp circuits. Here we need a very precise measurement. Therefore, we need a thin film technology for this type of circuit application. And here it is. The thin film resistor array, ACAS, was selected. The array is available in either 2x or 4x configuration. And the resistances with up to a 1 to 100 ratio and matching tolerance down to 0.05. So like I said, very, very precise. In terms of temperature coefficient or TCR, you can get down to 5 ppm. To mitigate inrush current during vehicle startup with uncharged capacitor, banks in the load, another Vishay high voltage MOSFET, here you can see it labeled as TR13 in the schematic, was used. And also a power resistor labeled R4 here in the schematic. This is used for a two-stage pre-charge function. Here you can see it in the layout. The main pre-charge components are located on the top side of the board near the 12 main power switches. In the power circuit, Vishay's DTO35 power resistor was used. This is thick film technology in a 2 square package, and it's designed for very high pulse load applications. The nominal power rating is 35 watts, and this is for a 25 C case temperature, but must be derated for higher operating temperatures. And here you can kind of see one of the derating curves. Since the gate drive signal from the microprocessor to the pre-charge MOSFET must cross the isolation barrier that we were mentioning, we need to select a component for galvanic isolation. Since this is just an enabled signal, though, that switches at a relatively low frequency, we use another optocoupler with a phototransistor output. Again, you can kind of see the red line indicating the isolation barrier. The Vishay BOMA 617A optocoupler was a good choice for this function, as it provides a very high current transfer ratio with a low input current and a high collector emitter voltage for switching the pre-charge MOSFETs. This optocoupler is also rated for 3750 volts RSM for the isolation voltage in conjunction with the SOP for a low profile package. Now let's turn our attention to voltage sensing, since it's required in the pre-charge circuit to monitor output voltage and is also used in several other parts of the design. In this case, the high voltage is first scaled down using an integrated voltage divider by a factor of 200 by 1. A matched pair of resistors should be used for critical voltage measurements that are used for control or protection. Here you can see the component that was selected. This voltage measurement was accomplished by our resistor divider, CDMA 2512. It has a maximum working voltage of 14-15 volts and is offering a wide range of values and ratios with tolerances down to 0.5. And your typical TCR is 50 ppm. The divider comes in a 2512 package and can be offered with either a 3-sided wraparound or single flip termination. More on the schematic, and this is where Vishay really shines, is the voltage protection. So to protect the components from a higher voltage, a higher energy that could be introduced in either the 48 volt or the 12 volt bus, we need some transient suppressor. In this design, Vishay's unique X-clamp technology in conjunction with transient voltage suppression were used. Here you can see them in the schematic with D1A and D1B connected in series. This is just for reference. This is where the components are located, and they're placed on the output terminal and the power ground connection. This is really needed because you need to be very close to the transient source. Here you can see some of the transient voltage suppression that I was talking about. This is the unique technology that Vishay developed, and it features the snapback. More on this snapback behavior later. But basically, you know, when the working voltage is 24 volts, you need to have another component to go up to the 54 volts required for that could be seen in a 48 volt battery bus. Here are the graphs, the current versus voltage. The X-clamp suppressor has a much steeper slope compared to the conventional device, which results in a much lower clamping voltage for the same level of peak current. To obtain another working voltages, like I was mentioning, having the other resistor in series was required. All right, so this is for the power supply. And so we need a 5 volt input. So to save space on the board, an integrated buck converter was used. Here you can see that it uses a very small footprint of the PCB. So here are more details on the Vishay microbuck that I was mentioning. This is the part that was used for this design actually has a commercial grade, but the automotive version will be released later this year. It's basically an integrated design with both the control IC and both power MOSFETs in a 5x5 millimeter package. The other components required are a storage inductor and an output capacitor. Also, you need a small resistors for some of the control parameters. The output voltage is adjustable to any value down to 0.8 volts. And there will be two current options, the 10 amp and 15 amp. The samples for the automotive version are planned for Q1 of next year, so very soon. So I was mentioning about a storage inductor. Here you can see it in the schematic. In this case, a Vishay IHLP 2525 with a 22 microhenry inductor was selected. And this was all selected based on the microbuck datasheet requirements. So this is the Vishay IHLP family of inductors. They come in a wide range of sizes and heights, and with a very high current density. They feature powder iron construction, which was initially introduced by Vishay, which provides a very soft saturation, which can be seen in a later slide. These low-profile inductors can be also operated to a 180C. The IHLP technology, like I was mentioning, was introduced by Vishay, and it features a very unique construction. Basically, the copper wire was welded at a very, very high temperature, resulting in a very compact inductor. This is the graph that shows the saturation. of the IHLP compared to a standard ferrite. The powder iron technology is very stable as opposed to the ferrite in the red curve, which shows how the inductance value really drops or saturates, resulting in a very undesirable condition of an inductor. So it basically doesn't act like as an inductor anymore. Another advantage of the IHLP is the different materials that are available. Each material provides a different characteristic to accommodate to different requirements. For instance, here you can see the low DCR losses or even the high temperatures up to 180 C. This is another innovative design by Vishay. This is the IHLE. This features an integrated shield to mitigate electric field emissions that could result in EMC compliance. This shield also provides an extended shock and vibration performance than the standard IHLP. Also, it provides an improved due to the 4 pads used for mounting the such field. So here we can see the user interface. The Vishay eFuse can enable and disable using either the on and off buttons on the PCB or by an external controller, which we're going to talk about later in the presentation. Current limits can also be manually adjusted with a range of 1 to 100 amps, either with 2 potentiometers built in here, or like I mentioned, with an external controller. MOSFET is the external controller that I was talking about and can be used to control not only this eFuse, but also other Vishay reference designs. The MOSFET is connected using a 4-pin connector, and the RJ45 connector is used to make the connection to the computer. In the automotive industry, CAN bus is very popular, so the MOSFET can also be equipped with compatible chip and programmed according to the customer specifications. Instructions on this interface can be found on our website as well. In addition to the tools that I was mentioning, the complete reference design, the BOM, the Gerbers, the schematic are all available on the website. So in a summary, this new electronic switch and reservable fuse has for 48 or 400 volts. It can contain all the different features that we will cover during this presentation. As mentioned, a key feature to this design was the pre-charge function to limit any potential inrush to an acceptable level, and continuous current measurements for use for the vehicle's body control module. I know it was a lot of information thrown at you, but thank you so much for your attention. I hope it was informative, and please keep Vishay in mind for any component needs.
Yeah, thanks, Vince, for that really in-depth presentation. That was a lot of information. It's really interesting to me to see that there's such a wide range of circuit designs and components available to provide protection in different applications. We've got a lot of great questions already from the audience. I'll remind everyone there's still time to submit your questions, and we'll try to get them. Just type them into that Q&A section on your screen at the upper right. Vince, let's get started with the first question. How much parasitic inductance do the shunts come with, and do you specify that in your data sheets?
Yeah, I don't know the exact number on top of my head, but it is stated on a data sheet that you can find on our website.
Excellent. Okay. Next one is asking, can you use multiple sense resistors in parallel?
Yes, absolutely. Absolutely. Depending on the requirements, you can connect them in series or parallel.
Okay. This one is what accuracies do you see required for current sensing and voltage sensing in these applications?
The accuracy really depends on the component. Like I was mentioning, for some of the control circuitry, thin film was selected, so a very high precision. But for others, like the gate resistor, the MELF that doesn't have such a high accuracy was selected as well. So it really varies. It really varies on the application of the circuit. But like I mentioned, Vishay has, all the different resistors with all the different accuracies needed for a specific applications.
All right. And this one's asking about the availability of the PCB designs. Do you have the layouts available in your reference designs?
Absolutely. This is part of the all the tools that are included, with the reference design. That includes the bill of materials, the Gerber files, and the PCB design for sure.
And I'm just going to kind of follow up on that. That's probably just as important as getting the right component, because if you have the right components but you don't get a solid PCB design, it's probably not going to matter, is it, especially for these high power applications?
Yeah, absolutely. They all go hand in hand.
This one's maybe kind of similar, but maybe you got a slightly different answer for it. But how can I get the hardware of a Vishay reference design for testing?
This is through our distribution partners.
Okay, so is that like your development kit reference designs? Is that what they should be looking for?
Yeah, Vishay reference designs. So we have several designs available right now. Today we only talked about the eFuse, but we also have a smart battery shunt. We also have a converter, and we have an eMobility team that is developing more and more designs as we speak. But yeah, there isn't a specific part number to this reference design, so I invite everyone to go to our website and look for it, right? And if you don't know where to find them, please just contact your Vishay contact that can really point you in that direction.
All right. This one might be difficult to answer because I'm not sure what slide you were on, but what's the maximum output capacitance that the design can drive?
To be honest, I don't know it on top of my head. But this information can be found on the files that I was mentioning during the presentation. You can see all the different components, and you can see all the different specs, and you can kind of see. What I would suggest is, for specific questions like this, just look at the component, look at the specific data sheet, and then see why that component was used, right? For the requirement.
Mm-hmm. Okay. This question is asking about what are the slope of the current that you see arising in your example for an 800 volt eFuse, and what is the delay in the current sensing path that you designed for?
The current slopes.
So how fast is that current changing, I think, is the question in that design.
That is a good question, and that is something that we can include, in our in the materials for the eFuse designs for sure. Yeah, to be honest, I don't know it on top of my head. And today we didn't really cover the 800 volt eFuse. Today we covered the 400 volt. But yeah, no, great question.
Yeah, so reach out to Vishay and follow up with that one if you want more information. What would your recommendation be to simulate a slow but low fuse, for example, to allow for a transient in a BLDC motor?
To simulations. we have simulation models available. That is only, what I've seen so far is by request. It's this is a very specific simulation for a fuse. We don't have fuses per se. So this type of simulation would have to be accomplished by testing. Unfortunately, we don't manufacture fuses. This is just an integrated solution. So it has to be done through testing.
Okay. This question is asking, where can they find the reference design documentation?
Oh, this is fine on our website.
Okay. Is Vishay working on additional reference designs, such as an onboard charger?
Yes. Like I mentioned, we have an eMobility team in Italy. And as we speak, they keep developing and designing more and more reference designs for this popular subsystems in an EV vehicle that we have seen how popular they have become.
This one's, does Vishay offer SiC MOSFETs?
Yes, actually, this was a very new acquisition by Vishay. Vishay acquired a company called Max Power. And so right now we have a commercial silicon carbide available. The automotive, the world I live in, that's going to happen next year.
All right, well, keep an eye out for that then. This one's asking, are the components of the reference designs manufactured in China?
With Vishay, with the passives, we have a lot of redundancy all across the globe. So no issues there. When it comes to the semiconductors, there are plans, to have the back end of semiconductors, to have redundancy out of China. This question is becoming more and more popular nowadays due to the tariff. But yes, to answer the question, most of Vishay components have redundancy out of China.
I want to let the audience know here before we wrap up that in the handout section, upper right corner, you can download this slide presentation. Vince, while we give them a second to do that, I have a question for you. As an FAE, you kind of see a lot of different people's problems, and you have a good understanding of all the solutions. What is maybe the component or the solution that you think people aren't using enough in their designs?
The component, it really depends on the application. But what I would say is normally designers know Vishay for one component that they have used. Either they use a resistor, either they use a diode, and they associate Vishay to that particular component. But in reality, Vishay is a broader, is broader than that, right? So the answer to that would be, the component you don't know about that Vishay has, because Vishay is we call ourselves like a one-stop shop. So it can the Vishay can populate up to almost 80% of a PCB. So yeah, and in just to talk about some of the popular components that maybe could be used more or be considered more, where Vishay really excels is in transient protection. Like I was mentioning in the presentation, actually it has the #1 market share in automotive. So those TVS diodes are very good. Current sensing, inductors. So it's basically good technology. Vishay offers you a great quality and a wide range of products.
Excellent. Well, Vince, thanks for your presentation today and for the great discussion during the Q&A.
Thank you. And thank you everyone for joining.
Yes, thank you to our audience for participation. In just a moment, you'll be redirected to Vishay's page on All About Circuits. You will be able to view this session on demand by using the same link you used to view the webinar today. Thank you for your time, and we look forward to seeing you at another live session again soon.